Dora. I am from the University of Rio de Janeiro, the Federal University, and I've worked a lot with Mario de Oliveira. He's not here, but he's someone from StatMech, and we are going to talk about the configuration of rods, like larger rods within cavities, and some people ask me, well, where is São Paulo related to Natal? Well, this is Natal, this is where I live, Rio, this is São Paulo. They are 400 kilometers apart, and we are 2,500 kilometers from São Paulo. So we got to take a plane to get here. Well, this is a simple outline of what I'm gonna talk about. I have a motivation for that. I have a motivation. Okay, so then I'm gonna talk what the theory we do for that, to treat that, and then I'll tackle the problem and show you some results. This is, and that it is still an open problem. We have a lot of things to do. So I'm gonna end up the talk in a somewhat abrupt manner because there are some open questions. Well, traditionally, people like to talk about nematics within the concept in the context of bulk nematics. From the 60s, people started getting interested in the effect of boundaries when you have the nematic cells and the nematic effect. How do the mesogens, like the particles, behave near the surfaces? A little later, people got interested in those light shredder devices where you have pretty much the same problem. You have, for instance, in this case, you have a polymer matrix here, and then you have droplets of nematics, and those rods here can get oriented in certain direction, and then they let light go through. Otherwise, they won't get light go through. So they can probe light within the system, and most of the times they are constrained here within like a vessel or something. And people started getting interested in what's the effect of the boundaries on this nematic system. And what is important about that, what is relevant about that, is that in those cases you have like a small rod or a small molecule, and the container itself is like 1,000 or 100 times larger than that. And the theoretical framework for that is very well known, because you can use continuum theories where you have topological defects that may appear spontaneously, or they come due to the confinement and the imposed boundary conditions. And this is very well reported. There's a big interesting literature on that. And the problems are pretty well understood at this point. More recently, people started looking at larger mesogens, if you want to, larger particles. Those particles, for instance, this is an example. This is an F virus. Is a mixture of F virus with polystyrene spheres. The virus has like 800 nanometer size, and the spheres are 100 nanometer size in this system. They look for phase separation and formation of chains, and the containers, the vessels itself, like they are like 100 times, like 10 times larger than the particles themselves. Other systems are the filamentous biopolymers, where, for instance, here you have bundles of DNA and actin, and here you have some peptides. Once again, these structures are of the order of 50 nanometers within containers of the order of 1 micron, and that starts to be a problem when you have to describe the properties near the interfaces. That's my last example. You have like particles. Those are carbon nanotubes. You have those pictures are scanning from scanning electron microscopy. You have the columns. Those are lyotropic. You can understand as like lyotropic particles. Objects. And here you have declinations, very much similar to the small mesogens of simple thermotropic systems. So we pose these questions. How are we gonna describe the configurations? How did they? What's the configuration of those large particles in the vicinity of the container? This is a little bit exaggerated picture, but that's our problem. You can have like a rectangular vessel, you can have a circular vessel, and we ask what's the profile of those particles in the interior or outside of those vessels. So we have to meet, in this case, the continuum theories don't work anymore. So you don't have like a volume which is small to deal with continuous theories, but it's not small enough to have so many particles. So, in this case, we have to meet, there is always a trade between the packing between particles and the boundary conditions and the geometry of the vessel. So we want to describe the profile, the particle orientation as a function of the anchoring conditions, the concentration of the particles, and the particle shapes. There is no analytical solution for that. And here it's here what we have is they use a mixture of Monte Carlo and molecular dynamics to get that. So we have a colloidal liquid crystal made of rod-like particles constrained in a curved surface. And the order is controlled by excluded volume interaction. So what you have just excluded volume. And you have a fixed density. For each problem, I have a certain number of rods inside that surface. And I'm looking for the orientation profile there. So my approach is I consider a lattice bounded by a surface. And this lattice is formed by a stack of layers. Those layers I labeled by an index L. And on every lattice point, I have a particle. And my order parameter is the mean orientation of a rod on a given layer L. For instance, this is the mean quadrupole moment of a rod on layer L. So my order parameter with respect to the homeotropic anchoring is going to be this SL here. So this is how I describe the orientation of a rod within this lattice. Now, I'm going to restrict the orientation of this rod. It corresponds to a microscopic state of the three-state Potts model. This is just a generalization of an Ising model. What there is, you have like this rod that can be found in any direction, but I restrict this possibility to just 3 directions, like 1, 2, or 3. These 3 possible states can be vectors, or they can be just scalars if you want. But I translate those 3 states to the 3 possible directions, x, y, and z. And I solve this on a lattice. So I have to find a Hamiltonian that that describes what I'm looking for. So this is the Hamiltonian. So I'm gonna start talking about the curved lattice. So what I have here, I have those 3 first terms here. They are enthalpic terms, and this is my entropic term. This is standard Hamiltonian, and the way SL with an S, you see that this here, this is the interaction between a general rod on layer L and a general rod on the nearest neighbor layer. So a rod from staying here and a rod staying just above it or just under it. And this interaction here is negative. So if SL, SL plus 1 works like this, if they are oriented the same way, this is 1, otherwise it's 0. So this term forces an equal orientation between nearest neighbors, both on the same row and between neighboring layers here. So this forces them to be parallel. This is just this as well. This is just the interaction within one row. And this is the interaction between neighbor, this is nearest neighbor within this row, every row. And this is between different layers. This is just an external potential. I'm going to deal very little on that. This is the possibility of the surface to be chemically treated, prepared, I mean. This is the entropic term. I'm going to not talk too much about that. And I solve this both on a semi-infinite cubic lattice. I mean, I just treat, like I make a cut here, and I just study what's going on near the surface, and in a cubic surface and a spherical shell. So I do a mean field approximation for that, and I minimize that, and what I get is the orientation of a generic particle on layer L and I make an approximation that I detach one disk from the other, or one plane from the other. If I'm on a semi-infinite cubic lattice, I have independent layers, like sheets. Here I have independent disks. And because this is not a very serious constraint, because in mean field, the nearest neighbors just come just with a multiplicative factor. And mu is applied, as I said, just like a chemical treatment here, just on the first row. And I did numerically. This is a very simple numerical procedure. And here, those are just previous results that I made at the toy model just to study the cubic lattice. What I found is, now this is just to show that the boundary conditions on the surface, they are irrelevant. What counts, in fact, is my anchoring on the bulk. And this is what I have. This is the independence of the anchoring here. This is an important, I think it is an important result, showing that you have, within a certain temperature range, you have a first order transition, you have a coexistence of order and a disordered domain here. And I didn't say, but that's very important, theta is a normalized temperature and A is a normalized external potential. Oh, this is I'm going to talk at the end if I have the time. Well, now comes to the most interesting thing that I want to talk about is that the spherical container. What happens is that if you are very close to the surface here, those rods that have they have the number of rods you have here and the radius is such that they can either lay parallel flat here or they can point towards the center. So they can rotate this way here because there is enough room for them. And I have a stack of layers like this. I just draw one, but I have a region of particles that behave like this. Of course, when you go towards this region, towards the center of the sphere, you are going to get less and less room. So they are going to be more squeezed, and there's going to be less room for them. So being more squeezed, the exploded volume effect is larger, and they are going to be obliged to behave more orderly. That means that they tend to force a more order, a more configuration. So as you go there, because they press on each other, they are forced to point everybody towards the center here. Then you get to so you have a region for that. At some point where the number of if you say you have n particles in every layer, at some point the space for them it's smaller than B, which is this radial dimension. At this point, you cannot pack the same number of rods, and they are they have to be pushed to other layers. At this point, you're gonna start having disorder. So you start from a fairly disordered state, and you get order because of the excluded volume. At some point, they cannot support more because there is not enough room, and you start having disorder. Mm-hmm. Yep. No, They cannot move in radial direction, no. Yep. Yeah, in fact, I start off considering semantic layers, right? This is the structure, yeah. So this is just what I'm said in other words. Here, the radius of the disk is large enough so that I can accommodate n particles, n rods. L is this, so they can either be flat here, stay flat here, or they can point towards the center. This go on and on and on till I get to this radius here, where R over N is equal to B. So they are forced to be all parallel to each other, point to the center. And from there on, they get into a disordered configuration. Just repeating what I said, my index L increases toward the center. This is L equal to 0 and gets bigger and bigger. And this is like I have this set of disks. I have two constraints, is that particles in different disks don't interact. So I just take a surface here. And that I have n particles in every row of a disk. So I have n particles here, n particles in the next row, and the next row, and the next row. I'm gonna, at the end, I'm gonna release this constraint here, and I'm gonna, in a certain way, allow to change the number of particles from here to here. So, how I'm going to model that? I have exactly the same Hamiltonian as in the cubic case, but I have an extra ingredient, is that the interaction between neighboring rods increases as I go towards the center. I mean, I have a stronger excluded volume effect, and for that I have an L, which increases towards the center of the sphere or the disk. And I can propose many ways to describe that. For instance, I say that this EL behaves as L to a certain exponent gamma. And this corresponds, if you make a very simple calculation, that the EL depends on the distance. This is the distance between neighboring rods on the same row. That's the dependence. Okay, the interaction between nearest neighbor particles on a given row goes like this. Well, what's special about that is I get a novel feature. I'm going to find steps in the profile. And that has been seen a while ago by Distra. And I could, in principle, if I have a condition here on the surface which does not, which is not the mean condition, the same condition here, I could have just a smooth profile. Like it could be smooth, it could approach smoothly the bulk behavior. But that was not what I found. I found the presence of those steps. That means that I have some coherence, a local coherence here. So this is a toy system. So, and I studied how those steps, the size of those steps as a function of the interaction strength. So if EL is very smooth, I mean, it increases smoothly towards the center, I have a larger step. If it goes very fast, increases step, I have a shorter step. The width of those steps, they are also a function of the mismatch between the surface condition and the bulk situation. If I have a very disordered surface, which I describe by some certain temperature, here what I have? Oh, here I have in the bulk a certain degree of disorder, which is just 218, right? And on the surface, I have here this degree of disorder, which is very far from 218, right? I think here I change. This is actually, this 3 is the larger one. So when the mismatch is large, I have a wide step. When the mismatch is small, I have a narrower step here. Okay. This is just to show that the external potential here on the surface has no much effect on that. Everything is governed by the bulk here. Now, I'm gonna release the constraint that I have any particles in every row of a disk. So I want to have vacant sites. So in some lattice sites, I don't want a particle. So I want this way to control the concentration. So this means that I want to impose some quench disorder to my system, and I'm going to look for how I'm going to work with the 3-state model, Potts model with site disorder. But I didn't have much success on that because I myself couldn't work this out, and I couldn't find any good reference for that. It's very inconclusive. There is bond disorder, but not site disorder. So what I did is I tried to find a way to introduce disorder. And what I said is, when I work this out, I have to think of how many nearest neighbors I have here and I have here. So I put an H parameter that says the probability of having a nearest neighbor. So I account for the possibility of having not an unoccupied site on site. So I include here an H parameter that multiplies the epsilon here, so that I account for a vacancy. When I minimize that, what I found is that the introduction of this H doesn't affect much the expression for SL. It comes just as a renormalized factor here. It just, rather than E, I have an E, an epsilon, I have an epsilon H. So that means that everything that I found as a dependence of the temperature, I'm gonna find with H in the opposite direction. If I had first order transition, if I have, if I found a coexistence in a certain range of temperature, I shall find also a coexistence within certain range of concentration, a certain range of H's. So everything that I showed before is true also for the concentration. So in the simulations I mentioned, probably they should find also coexistence there. I mean, there is a ordered and a disordered solution for every shot that I show you on the Monte Carlo concentration, on the Monte Carlo simulations. Yeah, that's what I meant. So rather than saying this is certain temperature, I can say that this is valid for a certain concentration. Well, so this is do the simulation show this type of a coexistence within a concentration range? This is, I think, this is a question to be posed for people, to people that do with work with simulations. Now, at this point, we are trying to describe this type of problem where I have a solution and say you can have a sphere and there is an influx, there may be an influx of particles in the outer part of the sphere. So there is a chemical potential that pulls the particles into the vicinity of the sphere, and this is what we are doing now. Is like you have now two order parameters. One related to the concentration of particles, and the other one with the state, the number of particles and the orientation of the particles. So this is just an extension of this work that I just show you now. That's it. Thank you.